Hello everybody. This week what we're going to do is we're going to start off by looking at the rules of solubility and how you can determine if an ionic compound is going to be soluble or not without having to look it up on the internet. Now luckily you have a handy resource on the back of your periodic table. If you turn your periodic table over and look at the top center, you will see a box. I'm going to pop it up on the screen right there. And this box essentially explains which ionic compounds are going to be soluble in water, as well as which ionic compounds are not going to be soluble in water. Now, I would say there's not a ton of patterns or things here. So oftentimes you just have to read the table and look at the ionic compound you're given and just try to brain through whether or not that applies to one of the soluble compounds or insoluble compounds. But as you notice from the lesson, there are some general rules about what makes soluble and insoluble compounds. Alkaline metals often make soluble compounds. So that's like lithium, sodium, potassium, rubidium, and that kind of includes hydrogen as well. So you can include hydrogen when it comes to solubility rules there. Halogens generally make soluble compounds as well, though not with a certain number of different things, except for mercury being with chlorine, which is just an odd rule based on how the electrons organize themselves. Sulfate makes soluble compounds. Usually fluorine makes soluble compounds. Again, usually, except with alkaline earth metals. So it all depends on what the situation is. Insoluble compounds are generally made of hydroxide, but again, it's only usually insoluble. Put hydroxide with barium or lithium or ammonium or potassium and you get something soluble there. All right, so there's a whole bunch of different rules on there. Best way to do it, and that's why I want to do this video, is just to go through some compounds and show you what my thinking would be on whether or not they're soluble. Once we find a soluble compound on the list, we are going to write a balanced dissociation equation for it, again, based on what we did in the lesson. So the first compound we have on there is calcium hydroxide. Now, the minute I see hydroxide in there, you can see the first rule under insoluble compounds includes hydroxide. Hydroxide is insoluble unless it's with ammonium, barium, or a group 1A ion. And calcium is not ammonium, barium, or a group 1A ion. So this is actually an insoluble salt, and you wouldn't be able to dissolve this in water. Or you would be able to dissolve it, but at such a small amount that it would be nearly undetectable in water. The next one there is aluminum bromide. Now, again, the minute I see a halogen there, I'm going to immediately go to Rule 2 in the soluble compounds section there. Bromine is soluble unless it's with lead, mercury 2, mercury, or silver. Which is not one of the exemptions on the list here. So that means that this is in fact a soluble compound. So we have found something soluble in water. So what I'm going to do is write the dissociation equation for this and then make sure that I have it properly balanced. Okay, so I'm going to put my arrow here. Now the aluminum here is currently holding 3 bromines. Okay, so that means the aluminum has a charge of 3 plus, because it had to give 3 electrons away to the 3 bromines that were coming in. And there are 3 bromine minuses. Okay, that's part of the balancing, is because there's 3 bromines here, I'm going to have to make sure that I have 3 individual bromine anions on the right side. And we have a balanced dissociation equation. Essentially, when an ionic compound dissociates, as you guys know from the previous week's lessons, the cation and anion essentially fall apart and disperse themselves into the water as free-floating cations and free-floating anions. And in fact, there's 3 times as many bromine ions in the water when you dissolve it as there are aluminum ions. All right, perfect. Let's look at the next one. Now, those of you guys who were listening a little bit earlier in the lesson probably heard me mention mercury chloride. This is one of the very strange exceptions. Again, if you look at Rule 2 under soluble compounds, you'll see at the very end there, HgCl2 is soluble, even though chlorine is not soluble. Even though it says rather chlorine is not soluble with Hg plus 2. Bromine and iodine are not soluble with Hg2 plus either. But chlorine provides an exception to that rule and becomes soluble in water. This is another indication that solubility rules are difficult to come up with a hard and fast situation where you can just look at a compound and go, yep, that's soluble or not. As you guys know, the solubility often comes down to what the electronegativity difference is. So you'll find that a lot of these ionic compounds have a lower electronegativity difference when they're insoluble and a higher electronegativity difference when they are actually soluble. Anyways, HgCl2 is good to go. So we can check that off. That is definitely soluble in water. Let's draw our dissociation equation here. So we're going to put our arrow down. There's 2 chlorines per mercury. So we're going to have 1 Hg2 plus, because that mercury had to give 2 electrons away to the chlorine. And then we're going to have 2 chlorine minuses, because there are 2 chlorines there that accepted those electrons. And there is our balanced dissociation equation. The next one there is magnesium phosphate. Now, I know that seems like a pretty crazy looking ionic compound there, but remember what we have is magnesium cations that have given their electrons away to phosphate anions. Phosphate is a polyatomic ion on the periodic table that you'll see if you just go a little bit lower from the solubility rules. Phosphate is one that once I see, I know that it is the first thing listed in the insoluble rule number 2, and it says that phosphate is insoluble except with ammonium, NH4, which is not magnesium, and group 1A ions, which also is not magnesium, which means this one is in fact insoluble in water. Okay, phosphate can be soluble in water when it creates a compound, but in this case, it's not one of the, I guess, preferred cations that phosphate likes to be with so that it can dissolve. Now, the last example we have here is sulfuric acid. Now, we're going to talk about acids and bases a little bit later in this chapter in more detail. As far as acids and base solubility goes, we kind of treat hydrogen as if it is an alkali metal. So this is one of those cases where it does belong above lithium in the periodic table because it follows the same rules as a lot of the alkali metals when it comes to solubility. And I think we can probably figure out, without having to do much work here, that sulfuric acid is in fact water soluble because sulfuric acid is the acid dissolved in water. And it's actually these hydrogens that provide the acidity to the water. And we're going to talk about that in a little bit more detail in the next video. If you take a look at the solubility rules, you've got basically 2 rules you can look at. Rule 1 under soluble compounds says group 1A ions are soluble in pretty much every situation. And since we're considering hydrogen a group 1A ion for this, that makes it soluble. But as well, group 3 says that sulfate is soluble as well, except with those strange exceptions. It looks like lead, mercury, silver, calcium, strontium, and barium. And hydrogen's not one of those things. So either way you chalk it up, this is in fact going to be a soluble salt. Now, the only difference is because it's hydrogens and sulfates, you end up with an acid when it's done. Specifically, the acid is made up of 2 hydrogen ions or hydrogen cations and 1 sulfate anion, which is SO4 2 minus. Because again, the SO4 has taken 1 electron from each of the 2 hydrogens to get its stable octet, and the hydrogens have lost that electron so that it can feel better as well. Now, as I said, this is actually what creates the acidity. This is very, very reactive. A hydrogen cation is a floating proton. It's a proton because hydrogen only has 1 proton in its nucleus, and there's no electrons around it. So it's basically a free-floating proton, and those are very reactive, which is what gives acids their characteristic reactivity and corrosiveness. Sorry, that's a little bit blurry there at the end. Hopefully that makes sense. If you have any questions about any of this stuff, as you guys know, drop me an email anytime. I'd be glad to go over any questions you might have. Have a good one. Watch the next video. We'll talk to you soon.